Structure and interpretation of computer programs, bite size. 1.2.2 Tree Recursion. Another common pattern of computation is called tree recursion. As an example, consider computing the sequence of Fibonacci numbers, in which each number is the sum of the preceding two. So 0, 1, 1, 2, 3, 5, 8, 13, 21. In general, the Fibonacci numbers can be defined by the rule the fib of n is equal to 0 if n is 0, 1 if n is 1, and the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2 otherwise. So basically you pass n minus 1 to n and n minus 2 to the Fibonacci thing, and that's what we get. Okay, cool. We can immediately translate this definition into a recursive procedure for computing Fibonacci numbers. So we can define the procedure fib that takes input n to be conditional if n is equal to 0, return 0. If n is equal to 1, return 1. Otherwise, add the Fibonacci, otherwise call the Fibonacci function on n minus 1, and then call it on n minus 2, and add those together. So, this is what it looks like. Figure 1.5, the true recursive process generated in computing Fibonacci of fib of 5. So fib of 5, alright, so we go say it's not 0 or 1, so we go fib of 4 and fib of 3. Okay, so then it does fib of 2, fib of 1, finally gets to a number, so 1, and then it says, finally gets to a number, 0, 1, adds those together, 1, 1, 1, 2, adds those, so we end up 2 over here. And it does this all the way down over here, and you can see we do 3, 2, 1, 2, 1, 0, 2, 1, 0. Okay. Consider the pattern of this computation. To compute fib of 5, we compute fib of 4 and fib of 3. To compute fib of 4, we compute fib of 3 and fib of 2. In general, the evolved process looks like a tree, as shown in figure 1.5. Notice that the branches split into 2 at each level except the bottom. This reflects the fact that the fib procedure calls itself twice each time it is invoked. This procedure is instructive as a prototypical tree recursion, but it is a terrible way to compute Fibonacci numbers because it does so much redundant computation. Notice in figure 1.5 that the entire computation of fib of 3, almost half the work, is duplicated. In fact, it is not hard to show that the number of times the procedure will compute fib of 1 or fib of 0, the number of leaves in the above tree in general, is precisely Fibonacci n plus 1. To get an idea of how bad this is, one can show that the value of fib of n grows exponentially with n. More precisely, see exercise 1.13. Fib of n is the closest integer to, I have no idea what that is. Whatever of raised to the n, that symbol, raised to the n over the square root of 5, where that symbol is equal to 1 plus the square root of 5 divided by 2, so about 1.6180. Is the golden ratio which satisfies the equation that symbol squared is equal to that symbol plus 1. Thus, the process uses a number of steps that grows exponentially with the input. On the other hand, the space required grows only linearly with the input because we need keep track only of which nodes are above us in the tree at any given point in the computation. In general, the number of steps required by a tree recursive process will be proportional to the number of nodes in the tree, but the space required will be proportional to the maximum depth of the tree. We can also formulate an iterative process for computing the Fibonacci numbers. The idea is to use a pair of integers a and b, initialized to fib1 and fib0, and repeatedly apply the simultaneous transformation. A becomes a plus b, and b is equal now to a. It is not hard to show that after applying this transformation n times, a and b will be equal, respectively to fib n plus 1 and fib of n. Thus we can compute Fibonacci numbers iteratively using the procedure. Define the fib of n to be fib iter with inputs. Define the procedure fib that takes input n to be fib-iter, the procedure fib-iter applied to the inputs of 1, 0, and n. Define the procedure fib-iter that takes inputs a, b, and count. If count is equal to 0, return b. Otherwise, fib-iter, fib-iter, apply fib-iter to adding a and b. And a, and then count minus the count variable minus 1. The second method for computing the fib of n is a linear iteration. The difference in the number of steps required by the two methods, one linear in n, one growing as fast as fib of n itself, is enormous, even for small inputs. One should not conclude from this that tree recursive processes are useless. When we consider processes that operate on a hierarchically structured data rather than numbers, we will find that tree recursion is a natural and powerful tool. But even in numerical operations, tree recursive processes can be useful in helping us to understand and design programs. For instance, although the first fib procedure is much less efficient than the second one, it is more straightforward, being little more than a translation into Lisp of the definition of the Fibonacci sequence. To formulate the iterative algorithm required, noticing that the computation could be recast as an iteration with 3 state variables. To formulate the iterative algorithm required, noticing that the computation could be recast as an iteration with 3 state variables. Example, counting change. It takes only a bit of cleverness to come up with the iterative Fibonacci algorithm. In contrast, consider the following problem. How many different ways can we make change of $1 given half dollars, quarters, dimes, nickels, and pennies? More generally, can we write a procedure to compute the number of ways to change any given amount of money? This problem has a simple solution as a recursive procedure. Suppose we think of the types of coins available as arranged in some order. Then the following relation holds. The number of ways to change amount A using n kind of coins equals the number of ways to change amount A using all but the first kind of coin, plus the number of ways to change amount A through D using all n kinds of coins, where D is the denomination of the first kind of coin. To see why this is true, observe that the ways to make change can be divided into 2 groups, those that do not use any of the first kind of coin and those that do. Therefore, the total number of ways to make change for some amount is equal to the number of ways to make change for the amount without using any kind of the first coin, plus the number of ways to make change assuming that we do use the first kind of coin. But the latter number is equal to the number of ways to make change for the amount that remains after using a coin of the first kind. Thus, we can recursively reduce the problem of changing a given amount to the problem of changing smaller amounts using fewer kinds of coins. Consider this reduction rule carefully and convince yourself that we can use it to describe an algorithm if we specify the following degenerate cases. If A is exactly 0, we should count that as 1 way to make change. If A is less than 0, we should count that as 0 ways to make change. If n is 0, we should count that as 0 ways to make change. We can easily translate this description into a recursive procedure. Okay. Define the procedure count change that takes the input of amount, and then apply CC to amount and 5. Okay, the CC procedure to amount define. Define the procedure CC that takes amount and kinds of coins as input. And the procedure CC is, we check if the amount is equal to 0, and then we return 1. Wait. Or if the amount is less than 0, and kinds of coins is equal to 0, we return 0. Else, add TC applied to amount minus kinds of coins, kinds of coins minus 1, and an amount, and apply CC to amount minus the first denomination and kinds of coins, and then kinds of coins. Alright, define the first denomination kinds of coins as check if kinds of coins is equal to 1, return 1. If kinds of coins is equal to 2, return 5. If kinds of coins is equal to 3, return 10. If kinds of coins is equal to 4, return 25. If kinds of coins is equal to 5, return 50. I think that's what that means. Oh, I may be saying return wrong in there, but that's what that is. Okay, the first denomination procedure takes as input the number of kinds of coins available and returns the denomination of the first kind. Here we are thinking of the coins arranged in order from largest to smallest, but any order would do as well. We can now answer our original question about changing a dollar. Count change 100, 292. So let's try that. Count change of 100 does indeed return 292. Count change generates a tree recursive process with redundancy similar to those in our first implementation of fib. It will take quite a while for that 292 to be computed. On the other hand, it is not obvious how to design a better algorithm for computing the result, and we leave this problem as a challenge. The observation that a true recursive process may be highly inefficient but often easy to specify and understand has led people to propose that one could get the best of both worlds by designing a smart compiler that could transform true recursive procedures into more efficient procedures that compute the same result. I would like to see this in action, actually. I will leave that as another exercise that we will do.